Welcome to this week's first lecture. So in this lecture we are going to be doing the following. So we will first review what we have done for the steady state error, and then we're going to solve a single example. And probably, if time permits, I'm going to actually start reviewing the future topic in the course, which is going to be the PID controller. So let us review what we did for the steady state error. Remember, if we are considering the following system with the forward path transfer function g of s and the feedback path transfer function h of s, then we define this error signal e of t right at the output of this summation or the subtraction. And we define what we call the steady state error as the limit as time goes to infinity e of t. Okay? And we have seen in our analysis that the steady state error is really dependent on what happens with this multiplication g of s, h of s. And this multiplication is called open loop transfer function. So in our analysis, we have considered inputs that would have Laplace transform. This is r of t, and that is the input Laplace transform of r of t, r of s. And we have seen that actually these simple input types that we consider would have the Laplace transform, let us say, 1 over s to the k. If it is unit step, for example, this is 1 over s. So unit step means that k is equal to 1. Unit ramp input has k equals to 2, and unit acceleration or unit parabola has k equals to 3. Okay? So when we have this type of inputs, we have determined what we would have as the steady state error. So the smaller the steady state error, the better our control system is in general. So we want the steady state error to be small. And in general, that means that our input, our output actually is going to be able to follow the reference input more closely if the steady state error is small. So remember, last time we have derived these steady state error expressions for the unit step, unit ramp, and unit acceleration. So for unit step, the case k equals to 1, the steady state error was equal to 1 over 1 plus kp, where kp was called the static position error constant, and kp was just the limit of this open loop transfer function as s goes to 0. Okay? For the unit ramp, when k is equal to 2, we had a steady state error equal to 1 over kv, and kv is the static velocity error constant, and it is limit as s goes to 0, s times open loop transfer function. And finally, for k equals to 3, the steady state error was 1 over ka, and where ka was limit as s goes to 0, s square open loop transfer function. Open loop transfer function is g of s, h of s, which is dependent on s. And remember that this type of results, this type of steady state errors are dependent on the open loop transfer function via a quantity that we call the type of the system. And we have defined the type based on the open loop transfer function. So the type of the closed loop system is dependent on the open loop transfer function, and we are writing, remember, I have k s to the n, and I have tau 1 s plus 1 going until tau m s plus 1, and t1 s plus 1 going until tn s plus 1. This was called the Bode form of the open loop transfer function, and this n was called the type of the system of the closed loop system. So we are determining the type of the closed loop system based on the open loop transfer function. Okay? This is almost always the case. In control, we almost always know the open loop quantities, and we try to understand what happens at the end of the feedback. We are wondering about the properties of the closed loop. So we are given the open loop quantities always, and we are wondering about what would happen to the closed loop system. This is my closed loop system, and this is my open loop transfer function. In the steady state analysis, we are knowing the open loop transfer function, and we are wondering the steady state error of the closed loop system. What happens in the steady state when we close loop? So remember, we have made some tables depending on the type of the system. Here I'm not going to be repeating all of these tables, but I will just show you the trend here. For a system to give zero steady state error to an input with the Laplace transform 1 over s to the k, the system type should be at least k. Okay? Because remember, I have told you about the so-called internal model principle. It says that for a system to give zero steady state error to an input with a Laplace transform given like this, then that the loop of the system should contain that Laplace transformation for the system to give zero steady state error to that input. Okay? For our closed loop system to give zero steady state error to the function, to the input r of t, the open loop transfer function should contain at least this Laplace transformation 1 over s to the k. Therefore here, for a system to give zero steady state error so this is going to be my steady state error. I won't have any other row here. For the system to give zero steady state error to an input of type r of s equals to 1 over s to the k, the type of the system should be at least k, because in that case, I have in the open loop transfer function, I have a term like 1 over s to the k, and that makes the steady state error of the system equal to 0. Okay? So if I have higher order types, so higher types here for the system, then steady state error continues to be equal to 0. Because in these cases, the loop still contains the Laplace transformation 1 over s to the k. Laplace transformation of the input. What happens when we have smaller types? So when we have the type of the system one smaller than k here, the power of 1 over s in the input, then we always have non-zero but finite error. Okay? So it is either 1 over 1 plus kp or 1 over kv type of result, which is going to be non-zero but finite. What happens when the type of the system gets still smaller, like k minus 2? At this point, we start to get infinite steady state errors. Go back to the previous lecture and look at our tables. They will always have this type of form. So when we have the input 1 over s to the k in Laplace domain, at the k type of the system we get zero steady state error, and we continue to have zero steady state error for higher types of the system. But if I make the type of the system smaller, when the type is equal to 1 less than the input 1 over s power here, when we have the type k minus 1, then the system would always have non-zero but finite steady state error to that input. And if I try to make the type still smaller, then the system will start to have infinite steady state errors. So this table is going to go to the left with infinity, and it's going to go to the right with zero steady state errors. Okay? So this is our general result. This is a generalization of what we did in the previous lecture. So that was a review of what we did so far. The next thing that we're going to do is that so far we have seen the transient and steady state response characteristics. Now we're going to solve an example that would contain both of these characteristics in the same system. So now let us write example. So we have the following system here. I have K over S plus alpha and S plus beta square. So this is my control system. And you see that there are some parameters, K, alpha, and beta. So the task of the question is going to be to find what these parameters would be, or how we should set these parameters so that the system have the desired steady state and transient performance characteristics. The following facts are known. So the first thing that we have is the steady state error is non-zero and finite for unit ramp input. Okay? The second property that is known, or that we are trying to achieve, is that the closed loop system, the overall system here, is approximately second order and critically damped. All right? And the third characteristic is that settling time, it is the 5% settling time, is equal to 3/2 for the closed loop system. And the question asks the following: based on this information, based on these pieces of information, find alpha, beta, and K. All right? So this is our question. Now let us now try to examine these characteristics one by one. So the first characteristic is that the steady state error is non-zero and finite for the unit ramp input. Okay? What is unit ramp in Laplace domain? We know that R of S for the unit ramp is 1/s squared. All right? Therefore, in this table, K is equal to 2. So for a type 2 system, this type 2 or a higher type system, we will have 0 steady state error. For a type 1 system, we will have non-zero finite error. For type 0 system, we would have infinite steady state error. So, and the first requirement here is that the steady state error is non-zero and finite for unit ramp input. What does it tell to us? What does this requirement tell to us about the system? It tells us something about the type of the system. So this requirement means that the system type is going to be K-1. Okay? And here K is equal to 2. This means that the system should be type 1. Okay? If it was type 2, it would give 0 steady state error. If it was type 2 or higher, it would give 0 steady state error. If it was type 0, it would give us infinite steady state error. Non-zero, but infinite steady state error. Since the steady state error is non-zero and finite, we need to have a type 1 system. What does this tell about the open loop transfer function? The open loop transfer function, let me write, instead of GH, I will write open loop transfer function should be in the following form. K over S and some other terms here. Okay? So now let us look at that open loop transfer function for that system. Open loop transfer function is K over, this is G, and this is a unity feedback system, which tells us that H should be equal to 1. So GH, the open loop transfer function, is going to be K over S plus alpha and S plus beta square. So now what is necessary on these parameters for the system to be type 1? Remember, the type of the system is related to the open loop transfer function. This is the closed loop system type. Closed loop system type 1 means that open loop transfer function should have one S here in the denominator. Okay? Now, what are the possibilities here? I need to have a single S in the open loop transfer function in the denominator. If I have beta equals to 0 and alpha equals to 0 at the same time, then I'm going to have K over S cube. The system would be type 3 in that case, and it would give 0 steady state error to unit ramp input. And what happens if alpha is non-zero but beta is equal to 0? If beta is equal to 0, I would have an S square here. But since alpha is not equal to 0, this term will not affect the type, then the system would become type 2. And a type 2 system would give 0 steady state error to unit ramp input. So that is not what I want. So the only possibility that this property, closed loop system being type 1, would be satisfied is the case when alpha equals to 0. If alpha equals to 0, and I really do not want beta to be equal to 0. Okay? If alpha equals to 0 and beta is not equal to 0, then the system is going to be type 1. The closed loop system will be type 1, which is what I want. So I have already identified one of the parameters here in my system. Okay? Alpha equals to 0. And the resulting beta at the end, if it is not equal to 0, then everything will be okay. So now let us go into the second part of the question. The second property required is that the closed loop system is approximately second order and critically damped. That is telling us something about the transient response of the system. Okay? So the first requirement was related to the steady state response, which is the steady state error of the closed loop system. And the second performance requirement tells us that this is a transient requirement. And similarly, the third one is a transient performance requirement on the system. Okay? So now let us go into the details of the second one. The closed loop system should be approximately second order and critically damped. The first thing that I need to know here is what is the closed loop system? What is the transfer function of the closed loop system? What happens when I close this loop? What is the overall system that I get here in the closed loop? And I can actually learn about it by calculating the closed loop transfer function. G closed loop of S is equal to, I will calculate it using the feedback rule. So it is the open loop it is the forward path transfer function, K over S plus alpha. And I can immediately substitute here alpha equals to 0. So it is K over, instead of S plus alpha, I will just write S, and S plus beta square. Okay? This is the forward path transfer function divided by 1 plus everything in the loop. But in the feedback path, there is the only transfer function is 1, H of S is 1. Therefore, everything in the loop will just be equal to the forward path transfer function only, S plus beta square. Now let us fully calculate the closed loop transfer function. So it is going to be K over, if I equate the denominators and cancel the denominators at the end, I would get S plus beta square plus k. This is my closed loop transfer function, and if I expand this polynomial term here, I would get k over s cubed plus 2 beta s square plus beta square s plus k. So we see that the closed loop system is actually a third order system, and we are required to make this third order system an approximately second order system, and that second order system should be just critically damped. Remember the second order systems. If I have an underdamped second order system, my pole locations are like this. If I have critically damped system, I would have real poles at the same location. And if I have an overdamped system, I would have real and distinct pole locations. So here, what is asked from us by this question, the second part of the question? It is said that this third order system should be approximately second order. Therefore, that tells me that I need to consider here double dominant poles here. I want to approximate this system using a second order system, which means that I need to consider double dominant poles, and that second order system, that approximate second order system, should be critically damped. So what this means is that I need to have double poles at the same location, which are the dominant poles of the system. Where can be the third pole? For these double poles to be the dominating poles, I need to have the third pole somewhere here to the left of these critically damped poles. Okay, so if I had this system, if I had this pole instead here closer to the imaginary axis than these double poles, then I would have an approximately first order system, and it wouldn't be really critically damped or anything. It doesn't really make sense. So if I have a pole topology which is given like this, then I am going to have an approximately second order system, because these poles are dominating this third pole, and I have an approximately second order system, and that second order system is critically damped. Why? Because we have double poles exactly at the same location on the real axis. All right? So this is going to be my pole topology, and that is the information that I would extract from part 2 of the question. Okay? Now let us go into part 3. Part 3 tells us that the settling time of the closed loop system should be 3/2. And based on this, I need to extract some property related to the system. What was the settling time? Settling time 5%. Let me write here 5%, was equal to 3 times the time constant. And remember, the time constant is determined by the closest pole distance from the imaginary axis, the distance of the closest poles to the imaginary axis. So if this distance is d, then the 3 times the time constant is going to be 3/d seconds. Okay? And our requirement tells us that this has to be equal to 3/2. Okay? So what does this tell us? This requirement tells us that d should be equal to 2. Okay? The closest pole or poles to the imaginary axis should have a distance of 2 to the imaginary axis. So I have this pole topology, then where are these critically damped poles? If d is equal to 2, where are the critically damped poles? They are going to be at s equals to -2. Okay? And this pole should be to the left of -2 on the real axis. Can this pole be a complex pole? Can the third pole be a complex pole? The answer is going to be no, because when we have a complex pole for a system with with polynomial coefficients which are real, if we have a complex pole, then its complex conjugate should also be a pole. Okay? So if this pole was here, then I would have another pole somewhere here at the complex conjugate of it. Then I would have 4 poles in total. But our system is a third order system. I cannot have 4 poles here. So we have found the required pole locations. The dominant poles should be at S1 equals to -2, S2 equals to -2, and the third pole is somewhere. Let us say S3 is equal to sigma 3. Okay? And I know that sigma 3 should be less than -2. For these critically damped poles to be the dominating poles. Okay? So now I'm going to go into the solution after extracting this type of information. So what is the characteristic polynomial of this system? So the closed loop system, we call the denominator of the closed loop system transfer function as the characteristic polynomial. I have already told you this in one of the earlier lectures, and the characteristic polynomial is important because it determines the closed loop poles. And I need to have closed loop poles with this topology. Okay? So what should be the characteristic polynomial? So I need to have s cubed plus 2 beta s squared plus beta square s plus k. It has 3 poles, it has 3 roots, and both of the 2 roots should be at the same place at -2. So I need to have s plus 2 square here, and the third pole is going to be at sigma 3, s minus sigma 3 here. So I need to have this polynomial, the characteristic polynomial determining the pole locations of the closed loop system should be in this form, s plus 2 square and s minus sigma 3. What does this tell us? This tells us that this characteristic polynomial, I need to be able to divide it by this polynomial s plus 2 square without any remainder. Okay? And let us try to do this division. So I have s cubed plus 2 beta s square plus beta square s plus k. I'm going to divide this polynomial with s plus 2 square. S squared plus 4s plus 4. Okay? Let me do the division here. So I will here put an s. So it is going to be s cubed plus 4s squared and plus 4s. Let me do the subtraction. 2 beta minus 4 s squared, because s cubed terms will cancel, plus beta square minus 4s plus k. All right? Should I continue the division, or this is the remainder? We see that this is still not a remainder, because the remainder from this division should be at most order 1. Okay, so here I can still continue the division, and I'm going to do that. So I have 2 beta minus 4 here. This is just going to be it, and I would have, let us say, 2 beta minus 4 s squared plus I would have here 2 beta minus 4 s plus I would have 2 beta minus 4. Let me do the subtraction here. So it is going to be beta square minus 4 minus I would have here 8 beta and plus 16 s plus k minus 4 2 beta minus 4. Okay? Now is the division complete, or can I continue with the division still? Have I found the remainder, or I can still continue with the division? We see that here the largest order of S, largest power of S is 1, and the largest power of the polynomial here, S, is 2. So I cannot here add a constant because it's going to bring an S squared term. So this tells us that this is my remainder. And the remainder should be equal to 0 in this case. That means that I need to have this coefficient equal to 0 and this coefficient equal to 0. So beta squared, and I would have minus 8 beta, and I have here plus 12 equals to 0. And here the coefficient of S to the 0 is going to be equal to 0. That means K equals to 4, 2 beta minus 4. So now let us try to find beta. So I have this polynomial. So beta is the root of this polynomial. So I can write here as minus 2 and minus 6. And that means that I would have beta minus 2 and beta minus 6 is equal to 0. And there are two possibilities. Beta equals to 2 and beta equals to 6. Okay? So do we have two solutions? If I substitute this beta here in this K equation, I would find what K is. But are these two solutions equivalent, or do they solve the question? The answer is actually, unfortunately, no. So although I have double solutions for beta here, then that doesn't mean that I have found the required solution. So only one of them can be actually true. Actually, only one of them is the correct solution in this case. And how do I identify the correct solution? So I told you that our closed loop poles should be located according to this topology. So this third pole should be to the left of the dominating poles. For these two critically damped poles to be the dominating poles, this third pole should be located to the left of minus 2. Okay? So how can I find this sigma 3? How can I find where the third pole is? So the third closed loop pole would be obtained if I divide this characteristic polynomial by s plus 2 squared. But that is exactly what I did here. And I have found a division here. Okay? And the division tells me that this s minus sigma 3 is given like this. Okay? So I have s minus sigma 3 is equal to 2, I will write just s plus 2 beta minus 4. So the s's are cancelling. So sigma 3 is just 4 minus 2 beta. Okay? Now I will look at these two solution candidates. Beta equals to 2 and beta equals to 6. Alright? Which one would give me a sigma 3 which is to the left of minus 2, which is smaller than minus 2? So I see that if beta is equal to 2, then sigma 3 is equal to 0. If beta is equal to 6, then I have sigma 3 is equal to 4 minus 12 minus 8. So which beta do you think is the correct one? I see that if sigma 3 is equal to 0, this third pole would be exactly at the origin. It is to the right of minus 2. And in that case, we are going to see that our closed loop system will be actually unstable, but still these two poles would not be dominating at all. So therefore, this solution is not possible. We want the critically damped second order poles to be the dominating poles. As a result, this solution, this beta value, is not possible. So our solution is beta equals to 6, and the third pole is at minus 8. Okay? It is going to be here. What is the resulting K value coming from this solution? And I'm going to find the K value using the second equation that we obtained after the division. K is equal to 4 times 2 beta minus 4. So I would have here 4 times, beta is 6, so I have 12 minus 4, 8. 8 times 4 is 32. So this is the final value of K. So we have actually found these parameters to satisfy the performance requirements. Alpha equals to 0, beta is equal to 6, and K is equal to 32. Okay. So that finishes the question. So I will finish this lecture by talking about what we are going to do in the next lecture. In the next lecture, we are going to see something called the PID controller. So I have here, this is called the plant to control in control. Okay? So that is plant or the system that we would like to control. And here we have the controller in our system. In a standard feedback topology, we would have a system here like this. We would have a feedback loop, and we would have a system that is called controller. Controller has a transfer function, GC of S. So this GC of S can have many different forms. The simplest form is just a simple gain, which is K. This is called the proportional controller, but most of the time a single proportional controller might not be sufficient for obtaining a good performance from the system, from the overall control system. As a result, we need additional controller terms here, some additional parameters to adjust. So here is what we do. We add 2 more terms here in general, and these terms would be KDS plus KI 1 over S. Okay? So this term, this S term is called the derivative term, and this 1 over S term happens to be the integral term. S in Laplace domain means the derivative. So remember, when you have a function f of t, and if it is Laplace transform is capital F of S, when we take the time derivative of that function f of t, f prime of t has the Laplace transformation S times f of S. That means that multiplication by S means the derivative in time domain. That is here, this KDS term means the derivative controller. That is why we give this name to this term. And the last term is 1 over S. If S multiplication is the derivative in Laplace domain, then S division by S means the integral operation. So what does this mean for the controller? I can actually try to write what the input and the output of the controller system would be. Okay? So we have the input of the controller is usually the error signal. Okay? This E of t enters as the input to the system, and the output of the controller is called the input to the system, which is U of t. This is the reference signal R of t, and this is my output Y of t. So that is the system to be controlled. Input of the system is U, the output of the system is Y, and we establish a feedback loop here to select the input of the system. Selecting the input of the system such that some performance requirements are achieved is called control. And we do the control by putting here another system that is called controller, and it has some unknown parameters, K, KD, KI. This is in general called the PID control. This is the P term, this is the I term, integral term, and this is the derivative term. This makes PDI, but if you change the orders, you will get the PID controller. So this is PID controller. And when you look at the GC of S here, which is K plus KDS plus KI times 1 over S, the input of the controller is the error signal, E of t. The output of the controller is the input to the system. Remember, in control, we are trying to choose the input of a system to make it behave as we like. So here, this input selection is made by another system that we design as the controller. So that is the U of t. Okay? So I know what the relationship between U and the Laplace transform of this thing is U of S. Laplace transform of E of t is E of S. All right? I know what the relationship would be in Laplace domain. U of S, the output, is the transfer function GC of S times the input Laplace transformation. Okay? So we have just this. So I have K plus KDS plus KI 1 over S times I have the input E of S here. Okay? So in Laplace domain, the input-output relationship of a PID controller would be K times E of S plus KD S E of S plus Ki 1 over S E of S. So this is the relationship between the input and the output of the controller in Laplace domain. Now I would like to write the same relationship in time domain. So let us write U of t. If I want to write it in terms of the error signal E of t here, I need to take the inverse Laplace transformation. So here this is going to be K times E of t, proportional term, plus KD times, this is just a constant, it gets out of the Laplace transformation, S times E of S. What is the inverse Laplace transformation of that thing? If I assume that the initial error is equal to 0, then I would have, this is going to be E dot of t, okay? Or d over dt E of t, okay? The derivative term plus, and what about the inverse Laplace transformation of 1 over S times E of S? So what happens if I take the derivative of 1 over S E of S? In time domain, if I take the derivative, then this is going to be multiplied with S, and I would get E of S. Okay? So the derivative of the inverse Laplace transformation of this thing is E of t. That means that 1 over S E of S needs to be the integral of E of t. Because when I take the derivative of it, I would get E of S. Okay, in Laplace domain. Therefore, this means that Ki, and I would have here the integral of E of t. Okay, so I would just write it like this. Here I can put also t, but I don't want the integral variable to be confused with the integration limit here. So this is the time domain expression for a PID controller. We are multiplying the error signal with K in the proportional term. In the derivative term, we take the derivative of the error, and then we multiply it with a gain KD and add it to this proportional term. And finally, we take the integral of the error from 0 to t, and we multiply it with a gain and add it to the other terms. So we have a proportional integral derivative controller. And the task here in designing a control system would be to satisfy the performance requirements by selecting these constants, K, KD, Ki. Okay? That is called PID controller design. All right? So sometimes we use only some of these terms. Okay? For example, this is a PID controller. How would a PD controller look like? How would we have a PD controller only? No integral term. In that case, the transfer function of PD controller would be looking like K plus KDS. What about a PI controller? In this case, the derivative term is going to be missing. That means that GC of S is going to be K plus Ki times 1 over S. Okay? A P controller is just K. PD is like this, PI is like this, and PID is like that. Okay? So this was just a crash course in PID controller. In the next lecture, we are going to learn about the effect of these terms. So what can we do by changing the proportionality constant here, K? What can we do by adjusting KD? And what can we do by adjusting KI here? Each of those terms would have different steady state and transient characteristics in the response. Okay? And we are going to learn how to adjust these terms, or what the effects of these terms would be in the transient and the steady state response performance of the system. But that is going to be all for this lecture. Thank you for watching.